Okay, let's unpack this. Imagine holding just two seemingly jumbled lists of numbers. They look linear, simple,
Uh-huh.
but hidden within them is the complete, complex, nested structure of a binary tree. Your mission, should you choose to accept it, is to take these two lists and reconstruct that tree.
Yeah.
That's the fascinating puzzle we're diving into today. How do you actually rebuild a binary tree if you're given, say, its pre-order and in-order traversal sequences?
And what's truly captivating here, I think, is that while a single one of those traversals alone is ambiguous, you could build multiple different trees from just a pre-order sequence, for example.
Why, it's not enough information.
Exactly. But this specific combination of pre-order and in-order provides exactly the unique blueprint you need. We're drawing our understanding from the source material, specifically the section 12.3 Building Binary Tree Problem in Hello Algo. Our goal, really, is to break down the elegant solution presented there piece by piece, so you can not just understand how it works, but really why it works, helping you build this knowledge in a way you'll hopefully remember.
So the problem as presented is precise. You have the pre-order sequence, you have the in-order sequence for a binary tree, and crucially, we're told that all the node values are unique. No tricky duplicates to worry about.
Which helps a lot.
Yeah, and you need to construct the tree and give back the root node. It feels a bit like being given two different maps that when you overlay them correctly, they pinpoint the exact starting location, the root.
And looking at this problem, especially how trees are inherently structured, it immediately suggests a really powerful algorithmic approach, the divide and conquer.
Right.
The source highlights why this fits so perfectly here. First, the problem is inherently decomposable. Building the whole tree, well, that's just building its left child subtree, building its right child subtree, and then, creating and connecting the single root node that sits between them.
Right, you can break the big tree problem into smaller, similar tree problems for the children. Makes sense.
Exactly. And the source correctly identifies that these subproblems are independent. Building the left subtree only requires the data and logic relevant to the left side. It doesn't interfere with or depend on the process of building the right subtree. They can essentially be solved separately.
Gotcha. And once those smaller problems are solved, their solutions combine to solve the original problem. You just attach the root of the fully built left subtree to your main root's left pointer, and the right subtree's root to the main root's right pointer. That classic pattern, decompose, solve independently, combine, it just screams divide and conquer, doesn't it?
It really does. It's a textbook example.
Okay, so we know divide and conquer is the strategy, but the real puzzle, the core insight, is how you actually use these two different linear lists, pre-order and in-order, to figure out where to make that crucial split.
Yeah, that's the thing.
How do you find the root of the current tree or subtree you're working on, and then from those lists, know which numbers belong to its left side and which to its right? This feels like the key that unlocks the whole thing.
This is the key. And it comes purely from understanding the definitions of these two traversal types and how they, well, complement each other. Think about it. Pre-order is defined as visiting the root first, then recursively traversing the left subtree, then the right.
Root left, right. Got it.
So any pre-order sequence always starts with the root node of the tree, or subtree it represents, root, left subtree, right subtree. The very first number is your root.
Oh, yeah, that's straightforward.
And in order is defined as recursively traversing the left subtree, then visiting the root, then recursively traversing the right.
Left, root, right.
So an in-order sequence always places the root node precisely between all the nodes of its left subtree and all the nodes of its right subtree. Left subtree, root, right subtree.
So if the very first element of our pre-order list tells us the value of the root node we need to build right now,
Yes, that's the root. You grab that value.
then you look for that same value in the in-order list.
Exactly. Specifically in the in-order segment corresponding to your current subproblem.
And because in-order puts the root right in the middle, finding the root's location in an order tells you exactly which elements to its left must belong to the left subtree, and which elements to its right must belong to the right subtree. It's the perfect separator for the children's notes.
Precisely. Let's grab the example from the source to see this in action. Suppose pre-order is 39217 and in order is 93127.
Okay.
Step 1, look at pre-order. The first element is 3. So 3 is the root of the whole tree. We create the root node with value 3.
Simple enough.
Step 2. Now find 3 in the in-order list. 93127. There it is, right in the middle, index 1.
Okay, got it.
Step 3, everything to the left of 3 in order is just 9. This must be the list of nodes in the left subtree. There's one node there.
Just one node. Okay.
Step 4. Everything to the right of 3 in order is 1 to 7. This must be the list of nodes in the right subtree. There are 3 nodes there.
Okay, that's incredibly clever.
Yeah.
In order gives us the boundary by showing where the root sits. But how does that help us divide the pre-order list? Pre-order doesn't have that left root right structure. It's root left right.
Ah, right. This is the second part of the trick, connecting the 2 lists. We know from the in-order split that the left subtree has 1 node, 9, and the right subtree has 3 nodes, 1, 2, 7.
Yeah, we just counted those.
Now look back at the rest of the pre-order list after the root 3. What's left is 9, 2, 1, 7.
Right.
Because pre-order is root left right, the elements immediately following the root must be all the nodes of the left subtree followed by all the nodes of the right subtree.
Ah.
And since we know the left subtree has exactly 1 node,
From the in-order split?
the next one element in that remaining pre-order list must be the left subtree's nodes. That's just 9s.
Which matches. Okay.
And the remaining elements after that, 2, 1, 7, must be the right subtree's nodes. And look, there are 3 elements, which perfectly matches the count we got from the in-order split.
Wow. Okay. So pre-order tells you this is the root. And in order tells you, and based on where that root sits here, everything this way is left and everything that way is right. And hey, count how many are on each side.
Exactly.
And then you use those counts to carve up the rest of the pre-order list. That's the core division strategy. It feels like using one list to find the center point and its boundaries, and the other list to find the starting point and use those boundaries to measure out the segments.
You've got it. That synergy is what makes this pair of traversals so powerful for reconstruction. Now, to implement this recursively, we need a way to precisely define which segments of the original pre-order and in-order arrays we're currently trying to build the tree from at each step.
Right.
This is where index variables come in, acting like pointers to define these ranges.
So variables to say the current subproblem uses the data from index X to Y in this list and A to B in that list, like boundaries.
Precisely. The source uses a few key indices to track the current scope of the problem. First, we need to know which element in the pre-order array is the root of the current subtree we're building. Let's call this index I. When we make a recursive call to build a subtree, its root will always be the first element of the pre-order segment passed to it.
So I points to the current root in pre-order.
Second, we need to define the range of elements in the in-order array that belong to the current subtree. Let's use L and R to denote the start and end indices of this in-order segment. L, R, inclusive. This range contains all the nodes of the current subtree we're focused on.
L and R define the current window in order. Got it.
Third, and crucially, within this in-order segment, LR, we need to find where the root node's value, which we know is pre-order I, is located. Let's call this index M. Finding M is the key to splitting the in-order range.
Okay, M is the root's position within the LR in-order window.
Exactly. Now, armed with I, L, R, and M, we can figure out the indices for the next recursive calls, the ones that build the children. Let's take the left subtree first. To build the left subtree, its root is the element immediately following the current root in the pre-order sequence. So the root of the left subtree is at pre-order index I plus 1. This is the new I will pass for the left recursive call.
Makes sense. It's the next thing in pre-order after the root.
And its nodes in order are all the elements in the current in-order segment L, R, that are to the left of the root at index M. These elements range from L up to, but not including M. So the in-order range for the left recursive call is L, M1.
Okay, that seems clear. I plus 1 for the pre-order start, and L to M1 for the in-order range. What about the right side?
Right. Now for the right subtree, this index calculation for the root in pre-order is the one that sometimes requires a second look.
Uh-oh.
The root of the right subtree appears in the pre-order sequence after the current root and after all the nodes that belong to the left subtree.
Right, because pre-order is root, then all of left, then all of right.
Exactly. We know the current root is at pre-ordery. The next element, I plus 1, is the start of the left subtree nodes in pre-order. Now, the question is, how many nodes are in that left subtree?
We figured that out from the in-order split, didn't we?
We did. Yeah. All the elements in the in-order range LR that are to the left of the root at index M constitute the left subtree. The number of elements from index L up to M1 is simply M1L plus 1, which simplifies to ML.
Okay, so ML is the count or the size of the left subtree.
Precisely. So in the pre-order list, after the current root at index I, there are ML elements that belong entirely to the left subtree. And then immediately after those ML elements, the root of the right subtree must appear.
Ah, I see where you're going. So to find the index of the right subtree's root in preorder, you start at the current root's index I, you add 1 to move past the current root, I plus 1, and then you add the size of the left subtree, ML, to jump over all its nodes in the preorder list.
You nailed it. The preorder index for the root of the right subtree is I plus 1 plus ML. This is the new I we pass for the right recursive call.
Okay, I plus 1 gets past the root, plus ML skips the left subtree nodes. That makes sense now. Phew.
Yeah, it takes a second to click sometimes. And the in-order range for the right subtree is simpler. It's all the elements in the current in-order segment L are that are to the right of the root at index M. This range starts immediately after the root's index M and goes up to the end of the current segment R. So the in-order range for the right recursive call is M plus 1 R.
Right, M plus 1 to R. That's straightforward.
The source includes diagrams like figure 12 to 7, which really help visualize how these indices I, L, R, and M define the current subproblem and how they get updated. Understanding that M represents the count is really the key to unlocking that right subtree preorder index.
Okay, we've broken down the problem, understood the core insight of using the two traversals, and figured out how to define the boundaries of the subproblems using these indices. How does this translate into the actual recursive code that builds the tree? What does that look like?
So the heart of the solution is usually a recursive helper function. You might call it DSS, depth first search, or just build or something similar.
Okay.
This function basically takes the preorder sequence, some way to quickly find node values in the in-order list. We'll get back to that optimization and those key index variables, I, L, R, that define the current subproblem scope.
The current roots index in preorder, and the start end of the in-order window.
Exactly. The first thing this function must do is check the base case. This is crucial for any recursion, right? It's
Yeah.
how it stops.
Right, otherwise it runs forever.
Yeah. So if the in-order range LRR is empty, which basically means L has become greater than R, or you could check if RL0, it means there are no nodes left to build in this part of the tree. In this case, the function simply returns null or none. It signifies there's no child node or subtree here.
Okay, stop condition handled. What if the range isn't empty?
If the range is not empty, we proceed with the recursive step, which has a few parts. One, we know the root of the current subtree is the element at preordery. So we create a new tree node using this value. This is the root node for this level of the recursive call.
Make the node. Check.
Now we need to find this root node's value within the current in-order range L, AR, to get its index M. Now, searching linearly through the in-order array every single time we need M would be really slow, especially for big trees. It could make the whole thing O and 2.
Oof, yeah, you don't want that.
No. So the source highlights a critical optimization. Before you even start the recursion, you pre-process the entire in-order sequence. You build a hash table or a dictionary or a map, whatever you call it, that maps every unique node value to its index in the original in-order array.
Huh. A lookup table.
Exactly. Using this map, finding the index M for preordery becomes incredibly fast average O1 time. Huge improvement.
Nice optimization. Okay, so we find M quickly using the map. Then what?
3. Once we have M, the index of the root in the current in-order segment, we know everything we need to determine the ranges for the children's subproblems, just like we discussed with the indices. So, we make the recursive call to build the left subtree. We pass it the original preorder sequence, the in-order map, the calculated preorder index for the left root I plus 1, and the calculated in-order range for the left subtree. That's the one.
Whatever that call returns.
Which will be the root node of the fully built left subtree. We attach it to the current root, left pointer.
Connect it up. Makes sense.
4. Next, same idea for the right side. We make the recursive call to build the right subtree. We pass the same sequences map, the calculated preorder index for the right root, I plus 1 plus ML, and the calculated in-order range for the right subtree, M plus 1R.
And attach its result to root. Dot right.
Attach its result to root.right. And 5. Finally, after the recursive calls for both children have returned, meaning that the subtrees rooted at root.left and root.right are now fully built. The current root node that we created back at step 1 is now complete. So we return this root node up to whoever called this function in the recursion stack.
So the main build tree function outside of the recursion just handles the initial setup, creating that helpful hash map for the in-order lookups, and then kicking off the very first recursive call.
That's exactly it. It starts the process with the root of the whole tree, which is at preorder index 0, and the full in-order range, typically 0, size 1. The recursive calls then handle the rest, breaking down the problem until they hit the base case.
And then the results get stitched back together as the calls return up the stack.
Precisely. The source's figure 12 to 8 conceptually illustrates this process. You kind of descend the recursion, creating nodes, and then you ascend back up, connecting them. And figure 12 to n visualizes how each recursive call is effectively focusing on distinct, smaller segments of the original traversal arrays. It's quite neat visually.
Okay, so we've traced the logic, the implementation.
Yeah.
Given this recursive approach and the use of that handy map, what's the performance actually like? How much time and memory does it take to build a tree with, say, n nodes? Does it chew up tons of resources?
Good question. And the answer is this algorithm is actually quite efficient, which is why it's, a standard technique. Let's break it down. For time complexity, we visit and process each of the n nodes in the tree exactly once. Each recursive call corresponds pretty directly to building one node.
Okay.
Inside the recursive function, finding the root's index using that pre-built hash map takes, on average, one time, constant time. All the other operations, checking the base case, creating a node, calculating those indices, making the recursive calls, they all take constant time per n as well.
So constant work per node.
And there are n nodes, so the total time complexity is O(n). It scales linearly with the number of nodes, which is generally considered very good.
Nice. What about space, memory usage?
For space complexity, there are two main things to consider. First, that hash table we create initially to map in-order values to indices. This map stores an entry for each of the n-unique node values, so it requires O(n) space.
Okay, space for the map.
Second, the recursion itself uses stack space, to keep track of the function calls. The depth of the recursion is determined by the height of the tree. In the best case, if you have a perfectly balanced tree, the height is logarithmic, O log n.
Which is small.
Very small. But in the worst case, if the tree is completely unbalanced, imagine it just looks like a linked list, all nodes going down one side, then the recursion depth can go down n levels.
Ah, so the stack could potentially grow to size n.
Exactly.
Yeah.
In that worst case, the stack requires O(n) space. So considering both the O(n) space for the hash map and the potential O(n) space for the recursion stack in the worst case, the overall space complexity is also O(n).
O(n) time and O(n) space. Pretty efficient overall.
Very much so for this kind of problem.
What a deep dive. We started with just 2 linear lists, identified the current root using the unique property of preorder,
First element.
used the position of that root in order to define the exact boundaries and sizes of the left and right subtrees,
The crucial split.
and then leverage those sizes to find the starting points for the recursive calls on the remaining parts of the preorder list. And we repeated this process, elegantly dividing and conquering the problem until the entire nested structure was rebuilt. It's a brilliant demonstration, really, of how understanding data structure definitions like traversals and applying a standard technique like divide and conquer can solve seemingly complex reconstruction tasks really efficiently.
Indeed. And the combination, like you said, the definitional properties giving the insight, the divide and conquer giving the structure, and then that hash map providing the crucial performance optimization, it makes this a really powerful and elegant solution. It shows how different theoretical and practical concepts in computer science can weave together beautifully.
So what does this all mean for you listening? You now possess the fundamental blueprint for reconstructing a binary tree from its preorder and in-order sequences. Think about the process. You've learned how to take 2 one-dimensional sequences and deterministically rebuild a complex, multidimensional structure.
Yeah.
It's like cracking a code where each list holds part of the key and the relationship provides the algorithm. You can look at those lists and, see the tree hidden within now.
And this raises perhaps an important question for you to consider. We use 2 specific linear representations here, preorder and in-order, and a divide and conquer strategy to reconstruct a tree. Could similar approaches, maybe using different combinations of traversals, like, say, post-order and in-order, which also works, or even entirely different linear ways of representing other complex structures or relationships, could those be used to reconstruct or understand those structures by applying a similar divide and conquer mindset? How else might understanding these different views or projections of data help you solve other problems where you need to piece something complex back together from its parts?